Hi, friends. My name is Jamie Gaskins, and today we're going to be talking about Hotwire. By now, many of you have seen Basecamp's Hotwire announcement screencast showing how to create a real working, real-time chat application with multiple chat rooms without writing a single line of JavaScript. By the end of this talk, my hope is that you'll understand some of the science behind the magic that was shown off in that screencast. Here's our agenda for this session. We're going to go over some of the pieces of Hotwire and how they impact how you build your application. So first, we're going to look at what Hotwire is. The folks at Basecamp call Hotwire an alternative approach to building modern web applications by sending HTML instead of JSON. Hotwire is an acronym that stands for HTML over the wire. The Hotwire website lists Turbo, Stimulus, and Strata as being its three main components. The first piece we're going to talk about is Turbo. Turbo provides the most basic building blocks for building Hotwire applications. Turbo used to be called TurboLinks, and its main purpose was to make web page navigations faster by preserving the rendering and JavaScript execution contexts so that the browser doesn't need to completely tear down and reconstruct those contexts every time you click a link. That's still here in Turbo, and you still get that functionality for free just by loading the JavaScript payload. It also provides what it calls frames, streams, and an action cable integration, all of which we'll go into more deeply in a few minutes. Even though Turbo provides a lot of functionality out of the box, your application may have some features that don't fit well into its capabilities. For those features, you can use the Stimulus framework to provide some custom functionality to fill in those gaps. We won't be going into depth on Stimulus because Hotwire doesn't actually change how you work with Stimulus controllers inside your Rails app. You still use them the same way you did without Hotwire. Strata is a bridge that lets you write native mobile apps using web technologies. The Basecamp team haven't really elaborated on this, but if I had to guess, it's likely an API similar to some of the things that you'd find in the React Native ecosystem, such as native push notifications, integration with your photo library, or maybe some of the other sensors and APIs that are available primarily in native apps. We won't be going over Strata during this talk because it hasn't been released yet, and we don't really have a whole lot of information about it. Another thing we won't be going over is how to compose all of these concepts we'll be learning to make a slick web app. For that information, you might want to check out any of these talks at RailsConf, listed in the order they appear on the RailsConf website. We are going to be looking at how the things they cover in their talks work under the hood. So that's a brief introduction. Now let's get to the fun bit. The first thing we're going to look at are turbo frames. So turbo frames are the primary building block for Hotwire. Mechanically, you can think of them as a chunk of your user interface, small blobs of HTML rendered into the resulting web page. In some web frameworks, these may be called components, and Rails calls small chunks of the UI partials. Components, partials, and turbo frames are largely all the same idea, and a lot of the time, partials are how you construct your turbo frames. So let's say you have an e-commerce application with a product catalog. The product catalog itself can be a turbo frame, and each product inside the catalog can also be a turbo frame. You can compose frames within other frames. And tucked up here in the corner, we have some secondary content that can also be considered turbo frames. In this case, it's our cart showing the number of items in our cart and maybe some order notifications. But why would we do this? If we have partials, what do we need turbo frames for? What makes turbo frames so special? So let's say we're on the product catalog page. When we hover over a product, it brings up an add to cart button. When we add an item to the cart, we want two things to happen. The first is we want the background of that particular product to turn green, like this other one that's in our cart, because that's the design language we're pretending is a good idea to indicate that we've added the product to our cart. And the second thing we want to happen is we want the badge on the cart to update to reflect the new item count in our cart. So let's consider what that would normally look like in a Rails app. We click the Add to Cart button, which sends a request to the server. The server twiddles some bits in the database and responds with a redirect. And that redirect may be to the same page we were on. It could be a pre-checkout page or some other page entirely. For the sake of simplicity, we're going to go back to the same product listing that we were on. So now the browser makes a second request after the redirect to get the updated page content. And the server responds with the entire page. The only things that actually changed were the one product and the cart item count, but we send the entire page. This can use significant server resources and potentially send a lot more bytes over the wire than we need to actually update the page. So if you're using turbo frames, though, it's pretty easy to get just those two things back. The rest of the page stays as it was, and we're only swapping in those two HTML snippets that we see down at the bottom here into the containers that we want them in. We look at how that works once we get a little further into the talk, because there's one more thing that we need to cover to learn how to process turbo frames in the response. Another thing we can do with turbo frames is to delay rendering until after the primary content loads. So like this secondary content up here, let's say, for example, uh, the cart item count and the notifications count take a fair amount of time to compute. Maybe the database table that they're in are the database tables they're in are massive, or the queries are very complex, or they may have to reach out to external services. When people are loading the product catalog, they're doing it so that they can look at those products and hopefully buy some of them. So we want to load that part as quickly as possible. We don't want to hold our customers back from giving us money. The secondary content can wait until after the primary content's loaded. And we can do this by pulling out the cart item count and the notification count badges and replacing them with turbo frame elements with an ID and a source attribute. That source attribute is what tells Turbo to fetch the content of the frame asynchronously after the page loads. When the request comes back, if there's a turbo frame element with the same ID in the response body, its contents get injected into this turbo frame element. One thing you might notice is that we're explicitly closing our turbo frame even though it's being loaded asynchronously with a source attribute. So you can render content inside of that frame to indicate that it's loading. Maybe you have a loading indicator or a placeholder element, um, because maybe you want to keep in mind that if you're loading secondary content asynchronously, you might want to provide a placeholder element to make sure that when the content comes back from the server, it doesn't move a bunch of content around when it swaps that content into the page. Trying to click something that then moves out from under your cursor because things moved around after secondary content loaded is a pretty poor user experience. We want to avoid that. But in our case, we're just loading badges that have no layout implications. As long as the HTML response from the server contains a turbo frame element with a cart item count ID, Turbo will insert its contents into this element. Rails also provides this helper method if you'd like to use that instead of an actual HTML tag. And when we add this action in our controller, our cart controller, um, it will respond to the request referring to the partial that we extracted the content for. And so when we see this on page load for our cart, we see this after that secondary request returns. And the request behind the scenes looks something like this. Notice we have this turbo frame header in the response saying cart item count. That's the turbo frame that we're trying to populate. The turbo JavaScript library makes the request for this content and it populates that header. So we can use that header to make sure that we provide the right turbo frame ID back in our response. And Rails uses this under the hood. And so there's still more that you can do with turbo frames, but we've still got a lot of ground to cover. So we're going to go ahead and move on to turbo streams. Turbo streams, remember how we talked about being able to send over just the content that changed on the page? Turbo streams are the concept inside of Hotwire that enable that functionality. This is the turbo frame for our cart item count after it's been rendered on the server. Notice that its ID is cart item count, and that's an important piece of information. When we set our response MIME type to be a turbo stream response with this content type header, and then our turbo stream payload looks like this. Its target attribute has the same as the ID is the same as the ID of the turbo frame that we want to update. The action is what we're going to do with the contents of this turbo stream. Here we're saying we're going to update the target frame, which means we're going to switch out its contents with the new stuff. The stream contains a turbo stream contains a template element. This element lets Turbo know that what's inside here is going to be the content that we're going to perform the action with. So we perform the action on the target with the template. In this case, the new contents of the cart item count turbo frame will be just this span with the updated count. The turbo stream for the product index item is very similar. It's rendering the new markup for the item in the product catalog. In this case, the action is replace. This just means that we're not just replacing the turbo frame contents. We're in this case we're replacing the turbo frame itself. There's no reason we have to use replace here. It just gives us an opportunity to show a different action that we can perform. Since we're using replace, we would need to also include the turbo frame element itself. Otherwise, future updates to this turbo frame won't be applied because it was replaced with something that doesn't have the turbo frame with this ID. And these are, we looked at update and replace, but there are 5 actions that TurboStream can perform out of the box. Update will swap out the contents of the target turbo frame with the stream's template contents. This is equivalent to setting the inner HTML property on the turbo frame element with JavaScript. The replace action swaps out the turbo frame itself, not just its contents. This is equivalent to setting the outer HTML property of the turbo frame. Append puts the contents of the turbo stream's template at the end of the target frame. This uses the JavaScript element.append method on the turbo frame element. Prepend puts the contents of the turbo stream's template at the beginning of the target turbo frame. This uses the JS element.prepend method. And finally, the remove action doesn't actually need a template. It just deletes the target turbo frame from the page. So we talked about updating both of these elements on the page when we add an item to our cart. You can send as many turbo streams as you like in a turbo stream response. This way, our application can make all the changes it needs in a single response. This way, we don't need to make two requests to the server in order to update both the cart item count and the new product index item, the new version of that product index item. And not all the turbo frames you specify here need to be on the page. Maybe you have a turbo stream endpoint that updates a lot of different turbo frames in various parts of the application. And that's turbo stream sent over plain HTTP responses. And next, we're going to get real funky with sending turbo streams carried across WebSockets with Action Cable. In order to use Action Cable with turbo streams, you need to import Turbo, Action Cable, and Turbo Rails into your application.js file. If all you want is Turbo and Action Cable, these are the only lines of JavaScript you need. You don't need to write any more. You don't need to define special Action Cable channels in JavaScript. It's all done via HTML and server-side Ruby code. Then in your HTML, there's a Turbo Cable stream source element that you can use to render that you can render to connect to Turbo Action Cable with Turbo streams. I wouldn't recommend writing the element by hand though. The Turbo Rails gem has an active record integration that base64 encodes and cryptographically signs the stream names for all the models that you broadcast updates for using your Rails secret key. So the browser just needs to be subscribed to that same stream name. This is not something you want to do manually in your views. But the Turbo Rails gem provides a turbo stream from helper to generate that Turbo Cable stream source element. It's super clean, and you can provide either a hard-coded stream name as a string, or pass an active record model to it, and it'll generate the turbo frame ID the same way it does, the same way that the Rails turbo frame tag helper does. The same way we saw before about how turbo streams have to target turbo frames by name, Action Cable streams have to be subscribed to the same stream name that your models are going to be broadcasting to. Everything in Hotwire hinges on the sending side and the receiving side agreeing on names. So now we have a bunch of turbo frames and Turbo Cable stream source elements on our page. What happens when you add a Turbo Cable stream source element to your page is that it opens a WebSocket to your Action Cable endpoint and subscribes to all of those streams that you have rendered Turbo Cable stream source elements for. We didn't write any JavaScript for this. All we did was render an HTML element. When we imported Turbo Rails into our application.js, this is one part of that JavaScript that we got. It's a custom HTML element that defines the behavior of the turbo cable stream source element. When we add the element into the page, the custom element's connected callback is invoked. The browser does this transparently. We don't have to do it ourselves. And that connects to Action Cable if it isn't already, and then subscribes to the stream. Likewise, when the element is removed from the page, its disconnected callback is invoked, and Turbo Rails automatically unsubscribes you from updates on this particular stream. So, for example, if one of your Turbo Stream responses filters some of the products from the catalog, you'll be automatically unsubscribed from those updates. You don't have to manually subscribe and unsubscribe anymore. Action Cable, the Action Cable integration in Turbo Streams handles it for you. So let's say you're working on a feature where if a customer has just purchased the last of a particular product in your inventory, you want to update the item in the catalog to reflect that so somebody doesn't try and add it to their cart. Inside the checkout process, you can update all of the products that were in that customer's cart by calling this line of code on them. So what we're doing here is we're calling broadcast replace to on the product, and we tell it which stream to broadcast on. In this case, it's the product index item with the product ID, and which partial we're going to render to Action Cable, and what local variables we need to be available inside that partial. Next, we're going to look at the trade-offs between Hotwire and single-page apps built with a front-end framework like React, for example. The trade-offs that we're going to look at are things like the effort required to build each app, how latency affects them differently, differences in how quickly users can interact with them, performance on slow versus fast devices, and how the server communicates changes and the client responds to them. The first trade-off we're going to look at is engineering effort. There are a lot of ways we can look at this, but we're just going to look at a few for the sake of this talk. The first big one involves getting data out of the database and into a consumable form for the end user. We'll call this getting data from the database to the screen. Let's take another quick look at how this happens with Hotwire. We looked at it before, but we're just as a refresher. We send the request from the browser to the server for the product catalog, and the server responds with the contents of that page. When we add an item to the cart, we get only the HTML elements that need to be changed. But in order to understand the engineering effort that goes into this, we need to look a bit deeper into the interactions of all the objects in play. The dependency graph here shows most of the pieces of the puzzle. There's a bit more to it, such as the application layout template that defers the rendering of the cart item count, but I couldn't fit that on the slide. When we render the initial page, we've got our product's controller index action, which fetches the products from the database using the product model and renders them into the product's index template, which renders each product into a partial, which contains the turbo frame for that product. And when we go back up the stack, the product index template also renders the turbo cable stream source element that activates the action cable stream for this product. Going back up the stack, once we've done all that, our page is now rendered. When a product is updated, maybe due to fulfilling an order, decrementing the inventory count to 0, we may have a broadcast callback on the model, as recommended in the Turbo Rails gem. This callback would know which template it's rendering and which action cable stream it broadcasts to. And that's the dependency graph for rendering the products, the products on the page. When someone adds an item to the cart, we insert or update the cart item using the cart item model. And then the broadcast callback on the model knows to broadcast an update with the contents of this template. And again, render to a string sent to this action cable stream, which the cart item model does need to know about. Now that may sound like a lot, and there's a lot of dependencies there, a lot going on, but thankfully Rails conventions make this can make this significantly easier. This app has a multiple representations of a product in its UI. It's hypothetical, but you can imagine that even though we're only showing the product catalog, you can imagine it being rendered on a details page, product details page, in the checkout page, and probably in several other places. For models that aren't used in literally every other part of the application, this can be simplified a lot. For example, the code we saw before, where we specifically broadcasted the update to the product index for something a active record model that is not used everywhere, it becomes this very simple active record callback declaration. We just say it broadcasts. We don't need to specify IDs because Rails will infer those the same way form helpers do. We don't need to specify which partials to render to the action cable stream, or even which action cable stream it renders to. We also don't need to explicitly broadcast the update when we perform the action. The use cases for rendering a shipment are very simple, so this single element does all of that work for us. Things that are simple in Rails tend to be dead simple. But again, when you do have multiple representations, you need to specify those IDs, partials, and action cable stream names. Otherwise, you may end up rendering the wrong template when you update. So now we're going to look at how that works for a single page app, such as one built with React or another similar framework. The JavaScript side of this has more pieces, and everything is significantly more coupled. In our server rendered app, we had quite a few dependencies, but notice how most of them are flowing the same direction. In our JavaScript apps, the dependencies are kind of all over the place. And inside a typical React app using Redux, these four pieces here are often a dependency of the entire application. Components fire off actions, which then cause Redux to invoke the reducer to update the state, which tell React to re-render components connected to that updated state. This is how most React apps I've worked on have operated. When your app first renders the product list component, it might not have your products loaded yet. So it fires off a fetch products action, which hits the reducer, which sends off a request to the products index endpoint, which then loads the products from the database, serializes them with the product serializer, sending it back to the reducer, which fires off a load products action, because fetching and loading are two separate actions when you're doing asynchronous IO, which invokes the reducer again, this time it's updating the Redux state, which then re-renders the product list component with the freshly loaded products, and re-renders a product component for each product in that list. And this is just to load data from the server. There are conventions that help you circumvent some of the decision making here, but nothing that'll take away as much of the manual effort that Rails does. I would also love to show the WebSocket updates here, but I don't have any more room on this slide. So that's comparing the engineering effort. The effects of latency can be another big deal in your application. How you mitigate latency can mean the difference between somebody giving you money or closing the tab. Latency in your application can often be separated into several key metrics, which are all different based on whether we're measuring from the time a user first opens the page or whether they're navigating around by clicking links. This is a typical waterfall representation of how a web app loads. The browser connects to the server, and then the browser and server discuss how they're going to secure the connection with TLS. Then the browser sends the actual HTTP request, and the server uses that to generate a response with its chosen content type, sends it back to the browser, and then the browser renders that response. The reality is a lot more complicated once you start adding in things like load balancers, reverse proxies, caching layers, and all that. That's all pretty specific to your own deployment and infrastructure, but I just want to make sure I at least point out that even though we're going to get into a few gritty details here, that there are still things that we're glossing over. In reality, these are not all the same size. This is closer to what it looks like when you're sending HTML over the wire. The generate response step involves fetching a bunch of records from the database, transforming them into HTML using ERB, Haml, or Slim templates. And then after that, the server sends the response back to the browser. Until the browser renders, the user is looking at a blank screen when you're loading just an HTML body. With a single page app, the generate response step is a lot shorter because it's only serving up a static HTML page typically. So it seems like that might be a no-brainer, but that response isn't it's not doing anything. It's just because it's just serving up static HTML with a very minimal HTML template. It doesn't do anything useful until after we load the JavaScript, which we haven't done yet. So now we have to make another request for the JavaScript. Notice that the request slightly overlaps with the render. The browser can fire off the JavaScript request while it's still processing the HTML, which is pretty clever. It's not hugely impactful, but you may be able to shave off a few milliseconds here and there. Notice that the steps for receiving the response and executing the JavaScript are a lot longer. JavaScript payloads for single page apps are often pretty large. Generating it doesn't take very long because the file exists as a static file on disk. So it's a simple matter of loading it off the disk and then sending it over the wire. However, if the user is on a slow connection, this can still take hundreds of milliseconds or even several seconds, which can take just as long as the response in the HTML version, even though it's not generating anything truly. And then once we get to executing the JavaScript, this can also be a huge slowdown. If you're sending 1 meg of JavaScript over the wire, the browser is typically executing, 3 to 6 megs of JavaScript, which will block the UI until it completes. And even when it completes and renders, we still have no data loaded. So we're still basically looking at a blank screen, and we need to send off yet another request for the product catalog that we outlined in the last section. This is likely to incur the same generate response time that our HTML example did. One thing the single page app has going for it is that once all this is loaded, it can now show a loading indicator. I didn't include one here, but a production quality single page app should probably have one so that users aren't left wondering why there's nothing on the page for an unknown period of time. And this is one thing that a single page app can do better than an HTML app. When you first load an HTML app, if it takes a good long while to generate that HTML, the user is looking at a blank page until it's done. And the other way that we can measure effective latency is how quickly the app responds when you're clicking links and navigating through various parts of it. When you're navigating around an already loaded web app that uses Hotwire, you don't need to load all of your assets every time, but you do have to make a request to the server for every navigation. Turbo does implement a caching layer though. So if you have a cached version of the page with that URL, it will render the cached version first while it loads fresh content in the background. And it does this the exact same way that we saw before using the turbo frame source attribute. Exact same concept. Turbo also renders a loading progress bar at the top of the page, so you have some indication that the new page is loading. It also attaches a busy attribute to turbo frames on the page. So if you're loading content for those frames while the request is in flight, you can design a loading indicator for them. And when you're navigating around an already loaded single page app, conversely, there are a few different possibilities depending on whether your JavaScript build process is configured to use a concept called code splitting. Code splitting lets you load less JavaScript up front and wait to load other parts of that JavaScript payload only when you render components that need them. The great thing about this approach is that it typically reduces first load time. But loading the JavaScript app all at once means you already have the entire app loaded when you're navigating. The trade-off of code splitting is that you have to make round trips to the server when you need that JavaScript, which will possibly make cascading requests for data after that. So you effectively lose the latency advantage of navigation until all of those components have been loaded and cached. If you're not using code splitting, though, your application is likely to be blazing fast as you navigate, since it's simply re-rendering content that it already has in memory. It doesn't need to invoke the HTML parser because it creates the UI elements using DOM APIs directly, saving potentially dozens of milliseconds. The only time that you end up having to wait is when it needs to fetch more data from the server. And we talked earlier about how JavaScript payloads for single page apps can be pretty large. It's not entirely uncommon to see 1 meg or more of JavaScript being sent across the wire on a web page. When you're building a single page app, you often have to take the performance of your users' devices into account as well and provide smaller JavaScript payloads up front so that their phone that's older than sand can still evaluate the JavaScript in a reasonable amount of time. A fresh React app using the Create React App tool weighs in at over 2.5 times the size of a Hotwire application. Even if you're careful, it's still common to see JavaScript single page apps sending over 1 meg across the wire. And this results in the browser having to evaluate 3 to 6 megs of JavaScript because the browser doesn't execute code until after it's been decompressed. So It's really easy to overlook JavaScript payload size when we're building the apps on our laptops or desktops with extremely powerful processors. But people using them on phones may not have access to that kind of computing power. Once you add in your own components, application specific state management, and the dependencies you'll need to build a proper production quality single page app, it's incredibly easy to see this payload, this JavaScript payload over the wire exceed 1 meg. I've worked on single page React apps that actually sent multiple megs of JavaScript across the wire, resulting in 10 to 12 meg bundles when after they're decompressed. Comparatively, Hotwire is using JavaScript under the hood, even if you don't have to be the one to write it. But that JavaScript size is, like I said before, 2.5 times less than the equivalent baseline React app. A baseline Hotwire app that is only using Turbo, Action Cable, and Rails, those three lines of JavaScript that I said, if you're that you may not have to write any more than those 3 lines. If that's all you're doing, you can expect to send less than 16 kilobytes of JavaScript across the wire, and that decompresses it to anywhere in the 40 to 50 kilobyte range. A device can parse and execute 40K of JavaScript in a handful of milliseconds. But again, especially when it comes to mobile devices, you have to go back to the network latency impact. Even the fastest devices can't speed up an app that's running on a slow network. So server round trips are likely to still be your bottleneck most of the time. Whether you're using Hotwire or building a single page app, the server is still your source of truth for all of your models. And you have to send the representations back to the client when the browser sends a request to create, change, or delete one of them so it can have a fresh local copy. With Hotwire, you have a single layer to concern yourself with, and that's the UI. When you're rendering the same partial template that you rendered in the original request for the page. Beyond that, you may have to specify what to do with the model in that template. For example, append or prepend when you're creating a new record, remove if you're destroying, or update or replace the original if you're modifying it. But everything else stays largely the same. With a single page app, the server has to serialize the models over the wire. Then this single page app needs to deserialize it, stick it in some sort of JavaScript data structure, and then re-render all the UI components that reference that model. How this all wires up may not be trivial in your application, like we saw earlier. We looked at a React Redux example before, but you may choose to build a single page app differently. Other changes that they may come in over a WebSocket pushed from a server without the browser requesting it. In these cases, a single page app would need to perform the same set of operations, but the Hotwire app doesn't need to do much at all. In fact, setting up the Action Cable WebSocket with Hotwire and subscribing to that WebSocket for updates for a given model or some other concept is usually a matter of rendering a single Turbo Cable stream source element. It's important to keep in mind that these are just trade-offs. The idea isn't to claim that the Hotwire approach is better or worse than single page apps in general. These are just things to consider when you're trying to decide which approach to use. If your budget is tight, you're already rendering HTML, and your team doesn't have a whole lot of JavaScript experience, or time to first interaction is your most important metric, Hotwire may be a better choice for you. However, if you already have a solid API, or interaction latency after everything is loaded is your most important metric, then you may want to choose a single page app instead. But again, just because something works better for your specific use case, it doesn't mean it's the preferred choice for every single application. So take all this with a grain of salt. And so that's our agenda for today. If you're attending RailsConf virtually, feel free to hit me up in the Hotwire Demystified channel on the RailsConf Discord. You can follow me on Twitter at the handle shown in the bottom right-hand side of this page. And like, subscribe, and ring the bell for notifications. Kidding. Wear a mask. Not kidding. And enjoy the rest of virtual RailsConf 2021. Thank you for watching, and I hope to chat with you all on Discord.